Hello and welcome to the Octet rule, ions, and naming ionic compounds activity. So chapter 5 is the first chapter where we start to deal with compounds. And compounds are going to be the result of bonds forming. So how do bonds form? Well, that brings us back to this idea of valence electrons. So valence electrons determine the chemical properties of the elements. They're located on the outside, or in other words, the surface of the atoms. And so these are the ones that are related to all the sort of bonding behaviors and chemical properties of these elements. And we can figure out how many valence electrons an element has based on its position on the periodic table. So for example, all elements in group 5a contain 5 valence electrons. And all elements in group 2a contain 2 valence electrons, and you can probably see where this is going. Group 3a contains 3 valence electrons, group 4a contains 4 valence electrons, and so on and so forth for most of the elements. So the octet rule describes how these electrons, these valence electrons, are rearranged in order to make stable electron configurations. So in other words, these elements generally want to obtain 8 valence electrons in order to mimic the nearest noble gas, and the noble gases are extra stable. The two ways that they can do this are that they can transfer electrons and form ions, and this tends to be what occurs when we react metals with nonmetals. Or we can end up sharing electrons, and when we share electrons we form covalent bonds. This is what nonmetals do with each other. So I'd like you to pause the video now and please complete questions 1 through 3. Alright, welcome back. Let's talk more about ions. So metals tend to form positive ions. We call these positive ions cations. And they do this because usually the easiest way to mimic the nearest noble gas is for them to lose electrons. So for example, group 1a elements, if they lose 1 electron, they form a +1 ion. So all the group 1a metals like to form +1 ions. And that gives them the same electron arrangement as the nearest noble gas. In group 2a, these like to lose 2 electrons to form ions with a 2+ charge. And group 3a likes to lose 3 electrons to form a 3+ charge. And again, they do this in order to match the nearest noble gas. So where do these charges come from? Well, let's look at magnesium, for instance. An atom of magnesium, and that term atom means neutral in charge, possesses 12 protons and 12 electrons. So our net charge here is 0, because positive 12 and negative 12 sum up to 0. A magnesium 2+ ion, this contains 12 protons and 10 electrons. So in the process of satisfying the octet rule, that magnesium wants to give away 2 electrons, because 10 electrons is the same electron arrangement as neon. And if we still have those 12 protons, if we sum these up, we now have a net charge of 2+. The nonmetals, on the other hand, generally form negative ions called anions. And so the elements in group 7a need to gain 1 additional electron to match the nearest noble gas. They tend to form 1- charges. Group 6a needs to gain 2 electrons, so they like to form 2- charges. Group 5a needs to gain 3 electrons. They like to form 3- charges. And you might notice that group 4a is missing from this list. A lot of the nonmetals in group 4a, they like to share electrons rather than transfer electrons, so we don't tend to see many of those form ions. Tin and lead are exceptions, and we'll talk about those a bit later on. So looking at an ion of chlorine, which becomes a chloride ion, we give it that "ide" suffix when it turns negative. A chloride atom contains 17 protons, 17 electrons, for a net charge of 0. But that chloride ion, where we've gained 1 more electron to mimic the nearest noble gas, which I believe in this case would be argon, we've gained 1 extra electron. So we have 17 protons and 18 electrons for a net charge of -1. So I'd like you to now pause the video and complete question number 4 on the activity. Welcome back. One of the critical skills from this chapter is going to be naming ionic compounds. We're going to start out by learning how to name ions, and then from there we're going to put it together to name compounds and also in order to write formulae for these ionic compounds. So when it comes to naming the cation has a very simple naming system. The cation, the metal ions, named after the element. So sodium atoms form sodium ions, calcium atoms form calcium ions, and so forth. We do nothing to change the name for those. The anions, on the other hand, we will be changing make some changes to the names. And for the anions, we're going to take the first syllable of the element and then replace the end of the element name with the stem or the suffix "ide." So chlorine becomes chloride, oxygen becomes oxide, and so on and so forth. We'll be talking about this more momentarily. And so when we write the name for the ionic compound, we're going to write the name for the cation first, followed by the anion, and we'll be practicing that later on. So we mentioned that metals are given the same name as the element. The metal ions are given the same name as the element they come from. But some of the metals form multiple charges. And if this is the case, we need to specify what the charge is using a Roman numeral. And so which elements do this? Well, the majority of the transition metals do this. Transition metals are in the middle of the periodic table. They're marked with the B groups. And so, again, most of the transition metals form multiple charges. So we can't just say a chromium ion because we could have either chromium 2 plus or chromium 3 plus. And so we'd say chromium 2 to indicate a 2 plus charge and chromium 3 to indicate a 3 plus charge. And you might remember I said that we'd be coming back and mentioning tin and lead again. So tin and lead also form multiple charges. Although they're not in the transition metals section of the periodic table, they behave similarly. So these elements from the bottom of group 4A, they both form 2 plus and 4 plus charges. So we can't just say a lead ion. We have to say lead 2 or lead 4 to indicate which type of lead ion we're talking about. So I'd like you to now pause the video and please complete questions 5 through 7 on the activity. One of the complicated things about naming ionic compounds is we have what's known as polyatomic ions. And so polyatomic ions are what the name implies. Poly means many or multiple, and atoms are, of course, atomic. So polyatomic ions are ions that are made of multiple atoms. And so we have a list here. I'd like you to memorize all of these polyatomic ions. So I've picked several that are very common in chemistry, but also in biochemistry. These are all very important ions in biochemistry and whatnot. So make sure that you memorize these. These are also posted in Canvas. And so you want to memorize the formulas, the charges, and the names for these. So I'd like you to pause the video and please complete question number 8. Another important skill from this chapter is going to be converting from name to formula and formula to name for ionic compounds. So when it comes to writing the formula for ionic compounds, there's a bit of trickiness. And that bit of trickiness is we need to have the ratio, the smallest ratio possible, where the total amount of positive charge equals the total amount of negative charge. In other words, the charges have to cancel each other out. And so if we look at an example right here, if we want to make a compound of sodium and nitride, sodium's in group 1A, which tells us it likes to form a 1 plus charge. Nitrogen's in group 5A, which means it likes to form a 3 minus charge. And therefore, for these charges to cancel out, we'd actually require 3 sodium atoms for every 1 nitride atom for these to all sum up to 0 charge overall. So Na, and then the subscript 3 tells us there's 3 sodiums, and there's our nitrogen. So again, smallest ratio where we have equal amounts of positive and negative charge. Write the formula for copper 1 nitride. So copper 1, that tells us we have copper with a 1 plus charge, and nitride is in group 5A, so we're going to form a 3 minus charge on this. And so it would take 3 of these coppers to cancel out the charge on 1 nitride. So this maybe wasn't the best example because it's so similar to the previous one, but hopefully you guys see the trend here. We're always looking for the smallest ratio where the total charge of our cations cancels out the total charge of our anions. Again, these should sum up to 0. So copper with 3 and then the nitrides right there. So I'd like you to pause the video and complete question number 9, which is the last question on the group activity, and then you should probably shoot on over to the discussion section in Canvas and post any questions, comments, things like that. Get those points in that discussion board. All right, guys, thank you. Bye.